Computer Building Blocks, Unit 1, Module 1, Objective 2. I am Mr. Valdez. So today we're going to talk about the difference between combinational circuits and sequential circuits. We're going to take a look at some flip-flops, understand what they are. We're going to also look at some registers, counters, multiplexers, and decoders. We're going to take a look at how all of these different circuits work and the logic behind getting these circuits to work. So first thing we need to do is understand combinational and sequential circuits. What are combinational circuits? Combinational circuits are interconnected sets of gates whose given output is a function of the input provided. So a combinational circuit can have n binary inputs and m binary outputs. So you're not limited to one single output for a combinational circuit. We can define combinational circuits using the following. We could define them using truth tables, and for each of the 2 to the power of n possible combinations of inputs, the binary value of each of the m outputs gets listed. So what does that mean? That means that if we have 3 possible inputs, A, B, and C, we can have up to 2 to the power of 3 different combinations, and that will provide us with 8 outputs, because there are 8 different ways that A, B, and C could be combined when using binary. We can use graphical symbols, which is the layout of all the interconnected basic gates, and we can use Boolean equations. So each output is going to be expressed as a Boolean function of its input signal. So what are sequential circuits? Whereas combinational circuits allow us to implement essential functions, combinational circuits do not allow us to provide information on memory or state. So if we want to persist with a certain piece of information, we are going to need a sequential circuit. In a sequential circuit, the output that we currently see not only depends on the current input, but also on the past history of inputs. We will see this as we talk about flip-flops. So what is a flip-flop? A flip-flop is a simple sequential circuit, and all of these flip-flops have similar properties. Flip-flops are bistable, which means that they exist in one of 2 states, and they keep that state information or that state until it receives input that causes it to change its state. So as a result, a flip-flop is a form of 1-bit memory. Flip-flops always have 2 outputs, Q and not Q, which are of course complements of each other. We're going to take a look at 3 flip-flops: an SR latch, the D flip-flop, and the JK flip-flop. So we start with the SR latch. The SR latch is implemented using NOR gates, and on the right hand side we have the characteristic table for an SR latch. In our characteristic table, Q to the n plus 1 means next state, whereas Q to the n means current state. So we see here, just as we spoke about just now, we said that the outputs of our flip-flops are Q and not Q, and our outputs feed into our inputs. So let's assume that our output Q, which is the one that we look at in terms of output from a flip-flop, is currently 0. If we have a value of 0 going into reset and a value of 0 going into set, then it means that the output is going to retain its current state. If, of course, the value of Q is 0, then it means the value of not Q is going to be 1. If we decide to send a value along the set line, because the S stands for set and the R stands for reset, if we send a value of 1 along the set line, then we will take the value of 0, that is the current output, and pass it into the NOR gate along with this value of 1. 0 nor 1 is going to give us 0, which means that the value of not Q has now changed to 0, which means that the value of Q is now 1. And thus, our flip-flop has been set. If we want to maintain the state, of course, then no values will come in along the lines. If, again, we want to reset this flip-flop, we'll send a signal along the reset line, 1, and we will get the value of 0 from not Q, and 1 nor 0 is 0, which means that the value of not Q is now 1. So that's how our SR latch works. Next we move on to the D flip-flop. The D flip-flop addresses the problem in the SR latch where S is 1 and R is 1. Because if we take a look at the characteristic table of our SR latch, we notice that the value, the next state, is undefined when both set and reset takes a value of 1. You cannot set and reset a switch at the same time. Think of any light switch. You can't have the light switch on and off at the same time. So the D flip-flop uses what is called a clocked SR latch, where data is only changed on a high clock pulse. It also uses a single input in order to define the next state of the flip-flop. So the D in the D flip-flop name stands for data, because essentially you're entering the one bit of data that will be stored in the flip-flop. So in a clocked SR flip-flop, a clock generally provides a stream of values 0, 1, 0, 1, 0, 1 going into our circuit. So if the value is currently 0, even though we get a 1 along any one of these inputs, we have to wait until the high pulse of 1 before that value is granted access to the general circuit. Inside of a D flip-flop uses a single value. Let's assume that our clock input is going to be 1, and we will pass a value, assuming that this here is 0 and not Q is 1. We will pass a value of 1 to set this circuit to on. So if our clock pulse is high and our value of 1 is entered, upon reaching this AND gate, we will get a value of 1 which would have originally been the set line. We take the value of the current state of the circuit, 0, and pass that into the NOR gate along with the value of 1, and what is going to happen is that our output value here is going to change to 0 for not Q, which will force a change of 1 into our Q output value, the value that we take, the asserted value. If we want to reset if we want to reset this value, then we can take a value of 0 here to be entered from the data input. We have a NOT gate inverting the value that is currently inside of here. So what is going to come along here is going to be a 1 along the reset line. And along with that 1 in the clock pulse, we're going to get a 1 value here. If we take the value of NOT Q, because our flip-flop is currently set, if we take the value from NOT Q and we enter it into the NOR gate, we're going to get 1 NOR 0. This is going to give us a value of 0, which will force NOT Q to be 1. And the circuit has effectively been reset. So if we look here, this is how the D flip-flop works. The next state of our flip-flop is based upon the data that is entered. So when we enter a value of 0, the next state of our flip-flop is 0. When we enter a value of 1, the next state of our flip-flop is 1. Next up, we have the JK flip-flop. Unlike the D flip-flop, and of course just like the SR latch, the JK flip-flop also has 2 outputs. This flip-flop makes accommodation for the entry of 2 1 values as inputs to the circuit, whereas in the SR latch, that would have caused undefined behavior. When 2 1 values are entered into the JK flip-flop, what happens is that the circuit behaves as if it were a toggle function, and the output would be reversed. So whatever the current state of the switch is would be inverted. This means if the output Q of the JK flip-flop is 1, and the value 1 is applied to both J and K, then the output of the flip-flop Q would become 0. So let's take a look at the implementation of this. Again, this is clocked. This is our clocked input. So we have to wait until the clock pulse is 1 before we can even start anything. We have to wait until the clock pulse is 1 before we can even start anything. So this value of 1 will take us into this AND gate. Let's assume that our value of Q was originally 0, which means that NOT Q is 1, and we are sending a value of 1 along the J line. If we are sending a value of 1 along the J line, we notice that part of our input comes from NOT Q for the J line. The J line is currently 1 because the circuit is off. So we have a value of 1 here. And with all 3 gates providing 1 for us, we can go into this gate along this line, providing a value of 1 here. Now, with this value of 1 here, we have the value of 0 from the Q output, which is the current state of the flip-flop coming in, and we will take that value of 0 and pass it through our NOR gate, which will turn our value output of NOT Q to 0, which will mean that our flip-flop has gotten set to 1. Now, what about the toggle function? If we wish to utilize the toggle function, we could use a value of 1 along J and 1 along K. And again, that's where these inputs coming along the outside become important. Because what's going to happen is that on the high clock pulse, we're going to get the value of 1 passing into this AND gate. We have a value of 1 passing into from the input. But because this value is set right now, we get the value of 1 passing along the reset line, whereas a value of 0 read from not Q would have been taken and passed into what would have been the set line. So no value is passed here, and we have a value of 1 passing now along the reset line. We take the value of 0 from not Q, pass it into here. 1 nor 0 will give us 0, and that would mean that not Q gets set to 1, and we just toggled the JK flip-flop off. Now let's do the same thing again with a toggle while it's set off. With a toggle while it's set off, we get a high clock pulse. The clock pulse goes into this first AND gate. We have the signals coming in from J and K being 1, but we're reading the output of Q along this K line, and the output of Q along the K line here is 0. So we are not going to get a value passing along this gate. We're going to get the not Q coming in from below along the J line. So it'll pass along what was originally our set line, and then our signal from the J line coupled with the 0 from the Q output is going to make our not Q output correspond to 0 when we pass it through the NOR gate, and it will have toggled our switch on using our JK flip-flop. So if we look at the table, we see that the next state for when J and K are 0 is maintained. When we send a value along the K line, the switch sets off to 0. Along the J line, the switch sets off to 1. And when a signal is sent along both lines, whatever the current state of the switch is going to be not that. So this here is an invert current state. So these are the block implementations of our flip-flops with tables. So we can have a clocked SR latch where the value will go into the circuit along the high pulse of the clock. We have our JK flip-flop, which allows us to invert or toggle when a value of 1 and 1 are set along both lines, whereas in the SR latch, there's an undefined behavior there. And for our D flip-flop just has one single output. Whatever that output, single input, whatever that input is, it's what the output is going to be. So our next state is defined by what comes along from the data lines. So a past paper question on this would be, give 2 properties of a flip-flop and state 1 use of this device. So 2 properties of a flip-flop are that it can act as 1-bit memory because it's bistable, and it also has 2 outputs, Q and not Q. How do we use this device? We use this device as 1-bit memory. So next we go on to registers. And what are registers? Registers use flip-flops to store data in different ways. So a register is a digital circuit that can store 1 or more bits of data. And the 2 most basic types of registers are parallel registers and shift registers. Parallel registers, these are 1-bit memories that can be written or read simultaneously. So if we look at the diagram, we have data coming in all at the same time to a flip-flop. This is a D flip-flop being used as a register, and what we will do with this D flip-flop is that we will, of course, wait until the clock signal for loading a register is high, and once the clock signal is high and data is coming in, we can store information inside of these registers simultaneously. So if we had the values, let's say 0, 1, 1, 1, 0, 1, 1, 1, all of these values would be loaded into the registers at the same time. And the same can be done for reading from the register. Because we have multiple output lines, all of these values or all of this data that is inside of the registers can be read at the same time. A shift register accepts or transfers information serially. So a shift register is where data are input into the leftmost flip-flop, and with each clock pulse, the bits are shifted to the right. So if I had this is a 5-bit register. Let's say we had 5 bits of information to enter. So we can enter 0, 1, 1, 0, 1. Because this is a D flip-flop, when the first bit is entered, we'll store 0 inside of there. When the next bit, which is 1, is supposed to be entered, we release the bit that was in this first register to the second register. So this 0 gets shifted across here, and the value of 1 comes into here. When we have the next bit to be read in, the value of 0 gets shifted across, the value of 1 is moved to here, and the value of 1 is taken from here and placed into this register. So again, the same thing happens as we read data, and so data is shifted along serially. Next, we have counters. A counter is a sequential circuit or register. The value of the counter goes up by 1 up to 2 to the power of n minus 1, where n is the number of flip-flops in the register. So if we have 4 flip-flops, it means that we can store values from 0, 0, 0, 0, which is 0, to 1, 1, 1, 1, which is 50. Once this value is exceeded, the register resets to 0. So these counters there are 2 types. There are asynchronous counters and synchronous counters. In synchronous counters, all of the flip-flops change at the same time. Whereas in asynchronous counters, the output value of one flip-flop triggers a change or a cascade in the next flip-flop. So we will investigate an asynchronous counter called the ripple counter. A ripple counter uses a series of JK flip-flops in conjunction with a clock in order to achieve a count. We have where data is fed in from the left-hand side and ripples through the structure in order to get the count. So we will take a look at an example, and in our example, our least significant bit is going to be on the left-hand side. So what that means is that we will be looking at this value in the ripple counter, where this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. We would look at a counter that can go up to 15, because if you have one value of each, you're going to get 1, 2, 4, and 8, which is a maximum value of 15, right, when you add them all up. But the size of your counter is limited only by the number of flip-flops you have. So each additional flip-flop will double the maximum number of the counter. So this is our implementation of a ripple counter. Now it looks very similar to the register that we saw earlier, the shift register, but the shift register used a D flip-flop, whereas this ripple counter uses a JK flip-flop. Basically, our ripple counter basically allows us to, our clock values go 0, 1, 0, 1, 0, 1, 0, 1. Only on the fall of the high value can a value change. So let's see how a count is achieved. If Q0 represents 2 to the power of 0, Q1 represents 2 to the power of 1, Q2 represents 2 to the power of 2, and Q3 represents 2 to the power of 3, we can have where all of these values start off as 0. So 0, 0, 0, 0. Currently, we have a value of 0 in our counters. So we have 0. Our clock pulse gets a value of 1, and when that clock pulse is about to shift back to 0, it toggles basically the values inside of this counter to 1. So now we have 1, 0, 0, 0. Remember, this 1 represents 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. So if we only have a value of 1 in 2 to the power of 0, then we have 1, 0, 0, 0, and this value here is 1, whereas this value was 0. If you take a look at our structure, you'll notice that the clock is only connected to one register, one flip-flop. But each other flip-flop is connected to the previous flip-flop. So the rule for the clock stays the same as the rule for what's coming out of here. So only when the clock falls, only when the clock pulse falls does a value change. So we had the fall of the first one to create 1. Now when we have this 1 here, our clock pulse goes back down to 0, right? But what happens is that this pulse also falls, causing what is here to go to 1. So what's important to note here is the clock pulses. And remember, the rule is that on the fall of every clock pulse, we have a change. On the fall of the high of every clock pulse, we have a change. So when we had that first high, we got a change here. But what the rule also goes on to state that on the fall of every previous flip-flop, we also have a change. So if we have another clock pulse of 0 and 1 here, it means that this value goes to 0, this value goes to 1, this value stays at 0 because we have not had a clock pulse fall from here, and this value will also stay at 0. If we're reading up, 0, 0, 1, 0 is 2 in binary. Again, we have the fall of the clock pulse. So once our clock pulse falls, it means that our circuit has a change. So our circuit looked like this just now, where we had 1 and 0 here. If our clock pulse was on that 1 and it fell, it changed our clock pulse to 1. So this is now 1. This is still 1 because we have not had a fall here, right? If you look at the diagram, you'll notice that because of the fact that these are chained along with each other, it takes double every time for a clock pulse to happen. So along Q0, we have a clock pulse where we have 0 and 1. But we need to have 2 clock pulses before we can get a fall at Q0. We need to have 4 clock pulses before we can get a fall at Q1. We need to have 8 clock pulses before we can get a fall at Q2. And we'll need to have 16 clock pulses before we can get a fall at Q3. So once our clock pulse changed here, we go back up to 1. We still at 0 here, we still at 0 here. This is 3. We have our next clock pulse change. So this falls back to Q0, falls back to 0. Q1 also falls to 0 because we've had a complete up and down pulse here. And now, because this is the first time that the previous circuit fell, what happens now is that we got a clock pulse that pushed this to 0, pushed this to 0. But this now is 1. So we have 1 here and 0 here. So 0, 1, 0, 0 is 4 in binary. And we can keep counting with clock pulse changes. So what will happen? Again, our clock pulse goes up. So we get a 1 here, 0 here. We still at 1 here with a 0 here. This is 5. Our clock pulse up and down is complete. So we get a change on this side. So this is 0 again. This goes up to 1. This is still 1. This is 0. This is 6. Our clock pulse happens. This goes up to 1. So this is 1. This is 1. This is 1. This is 0. We have 7. And our clock pulse falls again. This goes down to 0. Because this had a complete fall, down to 0. Complete fall, down to 0. And because this had a fall, this now goes up to 1. 1, 0, 0, 0 is 8. And we can keep counting until we reach 1, 1, 1, 1. And at that point, we have no more circuits to store data. So what is going to happen is that when this clock pulse falls, because we have no more circuits to store data, this goes to 0, this goes to 0, this goes to 0, and this goes to 0. So we went from 15 right back to 0 where we started. Multiplexers. A multiplexer connects multiple inputs to a single output. Only one input can be asserted along the output line at any given time. So we have select lines, and we use those select lines to choose which input is asserted along the output line. A multiplexer with n select lines can take up to 2 to the power of n inputs. So because we have 2 select lines, we have now 2 to the power of 2 inputs. So we have 1, 2, 3, 4 inputs. According to which select line is signals come in, it chooses which input line is going to be asserted along the output line F. So if our signal input line is 0, 1, it means that we're going to select line D1. We're going to take a look at the implementation of this as a circuit. So just a bit of logic for implementing. The multiplexer can be implemented using an AND or AND NOT gates. We have the select lines connected to AND gates in such a way that for any combination of S1 and S2, 3 of the AND gates will output 0. And the 4th AND gate will output the value of the selected line, which is either 0 or 1. So 3 of the inputs are always 0, and we always have one output being asserted. So this is our implementation of the multiplexer that we saw up here. So our implementation indicates that we have some data that we want to pass along these lines. So these lines are always asserted. So let's assume that we have one along all of these input lines. And we want to choose, or we want to find out which input line is going to be asserted when we enter certain values along S1 and S2. So if the value S1 is 0 and the value of S2 is 0, then what happens is that the value of 0 passes along each of these lines, but this line, each line is also split and inverted. So we have 0 passing along the main line and 1 passing along each one of the not lines. So let's check for S1. For S1, if we are with gate D0, D0 is going to get a 1 along this line and a 1 along this line, along with the 1 from the data line. It looks like if this line will be asserted. Let's check it against the other lines. Because we have 0, and this 0 here will be asserted here, but for this one, 1 will be asserted. We have 1, this is 0. 1 and 0 is not going to allow us to assert. 0 and 1 and 0, 0 and 1 will not be asserted. And also, if we are along this line, 1 and 0 will not be asserted. So data from line D0 will pass through. Let's take a look at another example with the select lines. So one more example. Let's say, for instance, our select lines, we got the value of 1 and 0 along our select lines. So S1 inverts this value to 1. S2 inverts this value to 0. 1 and 0 and 1 doesn't allow to pass through an AND gate. So we continue. If we have 0 along this line, we have 0. We have S2 with 0 along this line, coming down to here, 0. 1 and 0, this line will not be asserted. We have gate D2 with a value of 1 coming along the main line. We connect it to the main line, so that's 1. And we have a value of 0 coming in along the, not 0. We have a value of 1 coming along the inverted line. And we connect it to the inverted line. So this gate will pass because we have 1 and 1 and 1. But let's just check and make sure, because we have the value of 1 coming along here and the value of 0 coming along here. So when a value of 1 and 0 is inside here, all other gates will not be asserted except the D2 gate. So our output will come from D2. So a CAPE past paper question. CAPE asked us to draw a clearly labeled block diagram of a 4-to-1 line multiplexer. A 4-to-1 line multiplexer would look something like this. If it's a block diagram, you draw a block and you label it 4-to-1 multiplexer. A 4-to-1 multiplexer will have 4 input lines, 1 output line, and 2 select lines, S1, S0, I0, I1, I2, I3, and we have an output line, F. So Next question. In a security system, 4 sensors must transmit data to a single line for alarm notification. Each sensor transmits data for 1 second. Explain how a multiplexer can be used for the purpose described above, and discuss how data from each sensor is transmitted through the alarm notification line. So we can use a multiplexer in this way, and I'll just modify the multiplexer that I have here by allowing our multiplexer to be connected to a clock. This clock is a 2-bit clock, which means that the 2-bit clock, if we have 2 bits in the clock, it means that our clock always goes 0, 0, 0, 1, 1, 0, 1, 1, over and over and over. So this 2-bit clock feeds information along the lines S0 and S1. Now, in our security system, we have sensor 1. So let's say this is SN1, SN2, SN3, and SN4. We have 4 different sensors, and if it is that we want to transmit data, this clock changes its value every 1 second, and it will read data from each one of the sensors and transmit it along our output line, which could be connected to an alarm. So if at any point in time a sensor sends a signal, a live signal, let's say a signal of 1, where 0 is where the sensor is dormant, if any sensor value changes from 0 to 1, you will get within 3 seconds that signal passing through the output line to activate the alarm. We have decoders. A decoder is a combinational circuit with n output lines, only one of which is asserted at any time. The line that is asserted is dependent on the patterns of 1s and 0s fed into the input lines. So a decoder has n inputs and 2 to the power of n outputs. So if we have a 3 to 8 line decoder, depending on the signal passed in to the input lines of the decoder, just like we saw here, one of these lines on the output side will get asserted. So if I put in a value of 0, 1, 1, then line 3 will get asserted, because this is the code that allows us to assert line 3. Let's see how this would work in a circuit diagram. So again, we have the code 0, 1, 1, and the value of A is going to pass along here, and once it's on this side, we have the value of 1 because it passed through an inverter. Right? So the value of 1 goes to A here, 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 and here. For A, the value of 0 will pass through and go to here, 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 and here. Now along the B line, the same thing will happen. For the B line, because the value of 1 was placed in, we follow the line down, and B will give us a value of 1 here, 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 and here. And B will give us a value of 0 thanks to this inverter. It will give us a value of 0 here, 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 and here. And C has a value of 1. And C has a value of 1, so it will give us a value of 1 along this line, along this line, along this line, and along this line. C will give us a value of 0 along this line, this line, this line, and this line. So now we have the inputs for all, but only one of these gates has an input where all 3 of these come in as 1, and that happens here at D3. So if we isolate D3's inputs, you'll notice that D3 is the only one that has a value of 1, 1, and 1 coming into this gate. So D3 is going to be asserted along our decoder. Every other gate has a 0 somewhere and will not be asserted. So let's draw a clearly labeled block diagram of a 2 to 4 line decoder as a past paper question. So a block diagram of a 2 to 4 line decoder, right? 2 to 4 decoder. We will have 2 lines leading out to 4 lines for our decoder. Right? So signal 0, signal 1, line 0, line 1, line 2, and line 3. A circuit is required for a television show game. The circuit must control 4 light bulbs, B1, B2, B3, and B4. Only one of the light bulbs can be on at any time. State how a 2 to 4 line decoder can be used in the circuit and explain how the bulbs are switched on. Okay, so we can use a decoder by allowing us to, let me just shift this. Oops. I'll shift my decoder here, and I'm going to erase the lines. So let's say we have 4 contestants, right? Our 4 contestants, contestant 1, each contestant has a button on their buzzer. Each contestant has a button on their buzzer. And each button has a code 00, 01, 10, and 11. And all 4 of these are connected to the same decoder. So all 4 of these are connected to the same decoder. So when you send a signal, it's going to send this code into the 2 decoder lines. What is going to happen is that whoever presses the button first, their signal will assert a light bulb. So it will choose which light bulb. It will choose which light bulb is going to be lit when the button is pressed, based on the code entered. And that's how we can use a decoder to achieve this result. So the 2 to 4 line decoder can be used in the circuit because if you assign each button its own unique code, the decoder will figure out which light bulb to illuminate. So, I thank you very much for going through this session with us. Recap. In this session, we learned about flip-flops, registers, counters, multiplexers, and decoders. We learned what combinational and sequential circuits were, and we defined all of these things, flip-flops, registers, etc., using combinational circuits. We identified that flip-flops are sequential circuits that require us to use the previous state of the circuit to get the current state of the circuit. We also learned that flip-flops are bistable devices that can act as 1-bit memory. For registers, we learned about parallel registers and shift registers. Parallel registers where all the data is loaded or sent at the same time, and sequential registers or shift registers which push the data along using D flip-flops. We learned about counters using JK flip-flops that would allow us to move from 0000 to 1000 to 0100, and we achieved that using JK flip-flops, which we learned when you send the high and low signal, it inverts the value, and that's how we're able to count. We learned what multiplexers were. Multiplexers being a device that allows us to send multiple inputs along the same output line. And we also spoke about decoders, which take in a signal pattern and asserts a line based on the signal pattern. Thank you very much. I am Mr. Valdez, and I will see you in the next one.